All right, so we're pressing through in Chapter 3, and we're a little ahead of schedule, so I revised the schedule and I pushed it out, okay? And I'll clarify today exactly what's in Exam 1, which is 1 week from today on Wednesday. This set of homework problems I had scheduled later, I pushed them over, and I didn't put a number here, so even though I'm numbering these, I can't get this back to you if you turn it in on Monday. I can't get it graded back to you before the exam. So this is what I'll do. I encourage you to do the homework. It'll be extra credit to the extra credit. Means if you missed some of these earlier homeworks, it could replace them. So, but we can't get it back to you before the exam. So if you're really interested, you'll get the solution to them up on Blackboard Learn, but maybe make a copy of yours and then turn in your work, okay? You keep a copy. You'll eventually get it back. That can be confusing. Is it confusing? Yes, sir.
No, I was curious, with the review gone, are you going to have a recitation?
Well, the review was a slack day. It's like to catch up or to do something, and so basically on the heat generation, I'll be able to cover it and then solve some problems. Okay? Any other comments, questions? Let's jump into it. So, okay, what did this allow me to do? I can spend a little more time on extended surfaces, which I remember when I was making this syllabus, I was thinking, oh, that's going to be really tight right there, as well as a little more time on numerical study of conduction. So that helps a lot, I think. Let's jump into the material. So this is where we stop for the first exam. Do not go beyond 3.5. Do not go into 3.6. That will be next exam, not exam 1. So everything through. All right? Does that make sense? Everything up until this point. Okay. Let's solve a problem. We have a composite wall consisting of 3 materials with one-dimensional steady heat transfer as shown in the figure. So this is material A, a slab of material B, slab of material C. This is the temperature of this surface over here of 20 degrees C. There's fluid on this side at 225 C with the convection coefficient. And the thermal conductivity and the thickness of each of these slabs is given. Did they tell us the temperature of this surface over here? No. That's actually what's asked. Determine the inner surface temperature, TSI. This temperature. Find that temperature. That's what we're asked to find. So a couple things. If somebody said, what's happening up on this boundary right here, what would you describe happening up on the top and on the bottom? It's insulated. It's one-dimensional heat transfer. Everything says it's 1D in the X going from left to right. There's no some in the X and then some going up. No, it's one-dimensional heat transfer going through the slabs from hot to cold. So sometimes you might put this in there. Now, this is always confusing. Somebody says, we're going to have heat flux, and if I multiply by cross-sectional area, that'll be the flow of heat. True? What's my cross-sectional area for this problem? 90% of you have it straight. There's about maybe only 5% of you that will struggle with this. You'll think that somehow L sub A factors into the area through the slab A. Does L sub A factor into that area needed for the heat flux moving from left to right? No. What does that area look like? Well, it looks like this, if I could try and draw in 3D, and those slabs go back where that's slab A, and this is slab B, and that's slab C. So it's this face area which is hard to show. See? Right? Okay, so don't get confused on the area. How are we going to solve this problem? How are we going to solve for that temperature, TS? Well, we're probably going to employ some sort of flow through a network. So think about having a resistor, node connected by resistors, and even out here we have a resistor for a convection. So 3 conduction resistors and one convection resistor. These nodes have temperatures. So this is the temperature infinity on the inside, or just T infinity of the fluid. We don't really have a T infinity outside. This is the unknown temperature Ts inside. I'm trying to calculate that. Maybe we call this the temperature at location 1, temperature at location 2, and then this is the temperature at the surface on the outside, and that's given to be 20 degrees C, and that's given to be 225 degrees C. And this is the one we're trying to calculate. But right away, we know that these resistors are all in parallel or series? Series. So the flow through this resistor is the same as through that one, through that one, through that one. So if I have 20 watts, it's going through each one of those. Now, the equation is Q will be equal to the temperature infinity minus temperature S naught, the total driving, what's driving the flow through the system, the total temperature difference, divided by the sum of those resistors. Why do you sum them? Because they're in series. They're in series. So that resistance would be 1 over HA, L over KA, and that L and the K are for material A, and the thickness and the thermal conductivity and the cross-sectional area for slab B, and the thickness and thermal conductivity in the area of slab C. Now, at this point, you're left with a dilemma. You like to work with flow being watts, but we don't know that area. It's not given. There's 2 approaches. You can assume that the area is just 1 meter squared, and then remember, hey, I just picked that. They didn't tell me it was 1 meter squared, but I'm going to assume it's 1 meter squared, and I'll treat it that way. Or the other thing you can do is you can think about, if I really am interested in flux, what do I have to do to this Q on this side? Divide by A. What do I have to do mathematically to keep the equation consistent? Divide both sides by A. So then I'll have Q double prime is equal to T infinity minus TSO divided by the sum of ARs. It's like a resistance, but it's the multiplication of the area times resistance. Maybe you like that, maybe you don't. Maybe you just want to assume the area is 1 meter squared and run with it. That'd be fine. Or maybe you want to think about, no, let's try and track flux through the system. If you're tracking flux through the system, then the temperatures stay the same. But what happens here, it's 1 over H. It's AR, not R. And when I multiply 1 over HA times A, I get rid of the A's. It's a little cleaner, maybe. And this is TSI, and this is resistance. But it's an area times resistance, L over K for material A. And this is L over K for material B. And this is L over K for material C, and that's the TSO, which is 20 degrees C. So I sum up those A sub R's. That makes sense? I'm going to need to scroll down. Sorry about that, but I just used all the space I have, so I'll have to scroll down and continue the solution to this problem. So when I scroll down, what I have is I'm going to stick in my numbers. I know I just took them away from you visibly, but that was 25 watts per meter squared degree C. That was what H is. And then we're going to compute the sum of all of these resistances, but let's go ahead and compute them individually first. What is that length, L? It's 0.06 meters divided by the thermal conductivity. It's 20 watts per meter Kelvin or degree C, either one. It's a change in temperature. So you can see the units are the same for each of these terms, and then it'll be 0.03 divided by 0.04, and then it'll be 0.04 divided by 0.6. And when I run them and turn them into numbers, I look at it, it's like 0.04, then I'm going to add it to 0.003, then I'm going to add it to 0.750. I like to put 3 digits after each number so I can compare them a little more visibly. And then this one is 0.066666, but just put a 7 there. All right. When I sum those up, I find that its total is 0.85967 meters squared, degrees C per watt, and a meter squared. Yeah, it's a meter squared there. All right. Well, what I can do is I can say, how big of a fraction does each one of these contribute? How much is the convection as a percent or a fraction of the total thermal resistance? And so I just come in 0.040, divide that by 0.85967, and I find that that fraction of resistance, thermal resistance, due to the convection is a whopping 4.6%. I do it for the slab A, 0.4. That's not 4%, it's 0.4%, less than 0.5%. And then the next one is 87.3%, and then the next one is 7.8%. So you get a little insight. This should sum up to approximately 100%, or if you keep all the digits, it will be. But you see what dominates the heat transfer. What dominates the heat transfer is the low thermal conductivity slab B. It accounts for 87%. Don't lose sight of some of these trivial engineering insights. I've seen it where you get a complex problem going and people start debating and they say, oh no, to do a better job, we really need to promote the heat transfer. We need to increase the thermal conductivity of material A. They'll start arguing. If you increase the thermal conductivity of material A, will it significantly reduce the overall thermal resistance of this system? The thermal conductivity of A is already pretty high. So it's, right? So, but if you could get a change of a little bit of the thermal conductivity of B, it would have a big impact. It's like, it's very important. Look at the percent of the resistance controlled by it. So if you want to increase the resistance, decrease case of B, or if you want to do the other thing, either make it more thermally conductive or thermally resistive, you play with that parameter, case of B. All right, now let's finish up this problem. What do is we calculate what is the flux through the entire system. Well, we said it was 225 minus 20, and we just calculated the sum of the ARs, 0.85967. So we calculate intermediate step. The flux is 238.5 watts per meter squared. Well, if that flux is going through it's going through this one as well. So now we just focus on the analysis on just that convective part. And so Q double prime convective is the H times T infinity minus TSI. I just calculated, all that work was to allow us to calculate Q double prime. So now that we know Q double prime and H and everything else, we can get the temperature of the surface on the inside is equal to the temperature of the fluid on the inside minus Q double prime divided by H. So it starts at 220. We subtract off the flux, 238.5 watts per meter squared, and divide by the H, which was 25. And we find that the temperature of the surface on the inside is a whopping 216 degrees C. I wish I could have kept it all in one slide. Hopefully that you followed that logic. Does that make sense? Okay. Here's a different problem, slightly different problem. This time, they change up the temperature. They give you this temperature, and they ask for what is that thermal conductivity. You can play this game ad nauseum, sort of take some information away and give some other information and then ask you to make the calculation, right? So I leave it as a challenge to you to say, okay, well, can I solve this problem? Same concept. I'm going to think about flows. Maybe it's better if you just, for the first time through, just said, I'm going to pick an area of 1 meter squared. That way I'm thinking watts transferred instead of flux. Okay? And it's all in series. Makes it a lot easier, doesn't it? So the scheme for this one is go ahead and from this information and this information, I can get the flow through the system. Once I know the flow through the system, I can get the temperature on this side, let's call it T1. Then I can also, thinking about this temperature, I can go backwards, sort of forwards to get T1, backwards to get T2. Once I know the delta T and I know the flow through that slab, I can get the thermal conductivity. I would do it in about 4 steps. What was the first step? Get Q. We know that Q goes through slab A. We know the temperature on this side of slab A, hence get the temperature T2. We also know the same Q goes through slab C. We know the temperature on this side of slab C, hence get T2. Now we know the flow Q also goes through slab B. I know T1, I know T2. Now I'll get K. Hopefully that was a good roadmap for you, okay? All right. We talked a little bit about effective thermal conductivity. You have a mixture of things. Maybe you could see the darker region, maybe it has one thermal conductivity, the lighter region, a different thermal conductivity. Well, as an engineer, you say, well, I think the effective conductivity, treating this as a homogeneous mixture, will be some function of the conductivity of the parts. You're exactly right. What is the one and only one recipe? There's not one and only one recipe for that. It depends on the configuration and how it's all down there. And there's a lot of work that people have done in studying effective conductivities of composites and porous material, etc. All I'm going to do is say effective conductivity should be appealing to you as a budding engineer. It's like, okay, I can see that. We're going to use effective conductivity when we have a mixture. Let's now talk about changing the coordinate systems. So we have a radial coordinate system. The first one we'll deal with is cylindrical coordinate system. So we have a pipe. Right here I've shown an illustration of the pipe. It looks like a copper pipe, and what do? They wrapped it with the insulation. They say it's going to freeze tonight, right? Could be the coldest night in San Antonio tonight. So watch your pipes, all right? Maybe there's a run on the pipe insulation in Home Depot and Lowe's tonight. But anyway, if you have a length of the pipe this way, L, so that's the length, the thermal conductivity of that insulating material, K, and you know the temperature on the inside, T1 at radius R1, and the temperature on the outside, T2 at radius R2, then you could do the following. You could solve for the steady state radial temperature distribution. You could calculate the rate of heat transfer through that layer. So you could solve for T as a function of R. You could solve for Q. And you could find that thermal resistance in this layer of insulation. To introduce the topic, let me try to put a point here and put the R as a radial system going out. And here is R1 and here is R2. And in our mind we know this is curved like this and curved like that, and that's where, but we're solving for the temperature distribution as a function of radius. A lot of times it's nice to plot temperature perpendicular to our spatial coordinate system. There's T. If the heat is flowing from a hot inner pipe to cooler outside, right? You're trying to insulate, prevent the heat loss from a hot pipe. The temperature 1 on the inside will be greater than the temperature 2 on the outside. Clicker question. When I'm looking to solve for T as a function of R, Do I expect the temperature profile to be like this, version A, or like this, version B? That's too dramatic. Let me try and put version A, version B, or version C. I don't want to make them too dramatic, but A is straight. It's linear. B is a little concave down. C is a little concave up. So what do you expect that temperature profile shape to look like? A, B, or C?
R is always perpendicular.
Yeah, this is going out, radially out from the center line. Everybody in? All right. Well, let's do this. I'm going to try and go increasing radius. Here's another radius. Here's another radius. Here's another radius. There's another radius. Let's think about Q. Oh, I forgot. What was Q for in this textbook? It's the rate of heat transfer. What units? Watts. It's like flow. Let's say that I know that passing around the radius R1 is 50 watts. How much is going to go around the next radius? Is it going to be 50 watts, more than 50 watts, or less than 50 watts? And then the next one, the next one, the next one, and let's even out here. So if I have 50 watts coming into the insulation, what comes out the insulation? Is it 50 watts, more than 50 watts, or less than 50 watts? It's 50 watts. 50 watts for the same length. I'm just not changing the length. Just pick 1 meter length, okay? And so it's the same Q going across. But isn't Q the product of Q double prime and A? Let's talk about the area. As I go from R1 out to R2, is the area through which the heat is being transferred, is that increasing or decreasing or staying the same? Increasing. So what does the area do? It's 2 pi r times L. L is that length in the axial direction. What is 2 pi r? Circumference. It's the length of the arc, the circumference of that circle, and going a whole 360 degrees, right? So if I take 2 pi r and then I back it up L, that gives me the area. So you see that as r increases, the area increases. But the product of area times the flux has to be a constant, because what's coming in is continuing to move through. So what's the flux doing as it goes out? The flux is going down because the flux is the product. Does Fourier's law work in cylindrical coordinate systems? Sure. Is that equal to minus k dt dr? Yeah. And so if the flux is going down with distance r, what is K, the thermal conductivity, changing, or the slope of the temperature profile changing? The slope of the temperature profile. So it was more severe here. It's less severe and less severe as you go out. So what's the best answer? C. Now, you may have a different way of explaining that. Hey, come on now. Are you joking me? Did I lose that many people? Or I should have maybe talked about it first. All right. All right. Well, I thought it would be just the opposite. I thought we'd have a lot of right answers on that. Does it make sense? Okay, I tried hard. Well, now that if I set that up, now it's just plug and chug mathematics time. So instead of belaboring the point and getting lost, here it is, Cliff Notes version. Let's just go through it. If I'm asked to solve for the radial temperature distribution, I start with this equation. Do you recognize it? What is its name? Is it the Fourier's equation or the heat diffusion equation? Clicker question. This equation, A, Fourier's, or B, the heat diffusion equation? A, Fourier's, or B, heat diffusion equation? Only 20 seconds. All right, I'm stopping. Ready to go? All right. This was to help make up for it. It's the heat diffusion equation. That's the starting point, right? That was the main thrust of Chapter 2, all this mathematical, and really it's a conservation of energy around each point in our material. All right, so this is the starting point. It's a beautiful, ordinary differential equation. It's second order. I need two boundary conditions. Now I'm ready to forget I'm an engineer and act like a mathematician. Separate, integrate to get one constant of integration. Separate and integrate to get two constants of integration. So here's my general form for the temperature distribution. It's kind of funny, but it picks up a log of R. That's what it's going to pick up if you do the math right. Our two boundary conditions are that I know that it's T1 at R1 and T2 at R2. Here's another clicker question. In this sketch, as shown, is T1 greater than T2 or T1 less than T2? Answer A, B, or even C. T1 equal to T2, as shown. You redeemed yourself, and there's always a comic. There's always just one person playing with me. I don't know who they are, but that's just the way it is. So, I tried to emphasize that. So T1 is greater than T2 in this sketch that I showed right there. Okay, and that's common to think about hot pipe being cooled. So the temperature's high on the inside, low. I think conceptually that's a little easier that way. Okay. You have these two boundary conditions. You solve for C1, you solve for C2, you stick it back into your general formula, and now that is, I would box that and say that's our radial temperature distribution right here. It still has that log of R, but it also has the log of R1 and the log of R2 tucked in there, and that's about as compact a form as we can get. All right. This is part B. What is the rate of heat transfer through the layer? What do you use? What equation is this equation? Fourier's law. We know that area is 2 pi RL, and we put in the derivative of T with respect to R. Some R's cancel, which is nice, and you get this equation for the flow. So that's our rate of heat transfer through the layer. You say, can you identify a thermal resistance for part C? Well, you just think about the general form analogous to Ohm's law. The current is equal to the difference in the electromotive force divided by the electrical resistance. Our flow is current. Our flow is not current for heat transfer. It's the rate of heat transfer. And the temperature difference drives it. And so you just do some name calling. You say, that's it. It's natural log of R2 over R1. What is R2? Outer radius. R1, inner radius, divided by 2 pi K. What's K? Thermal conductivity of material. And L, what's L? The length in that axial direction. So that's our thermal resistance. You ready to do it for a spherical? Same pattern. Same pattern, Professor. I understand there's a lot of hot pipes needing insulation. That last formula looks very good. I don't think there's a lot of spheres that need insulation. Au contraire. Anybody driven around and seen like a big tank spherical out there? In Texas, there's a bunch down, especially along the coast. They're building a couple LNG plants. And if you're going to store LNG, a lot of times you'll put it into a spherical tank because it's so cold, you want to minimize the heat transfer, so you want a large volume but a small area to escape heat. So a sphere has a good volume to area ratio, really good. Also, it can be pretty rugged, pretty intense for any pressure. It's pretty spherical. And but you can insulate it. So it is, yes, you can have an application where you have a sphere and there's a layer of insulation that's been added. Okay, so one thing to remember, what's the area for the sphere? Is that the right equation? The area for a sphere? And so as the radius goes out, that area goes up. What is this equation? Heat equation. Two boundary conditions. Separate, integrate, separate, integrate. Get a general form. Right here, this general solution with C1 and C2. How do I find those constants? Use the boundary conditions. There's my formula for C1, formula for C2. Substitute, and there's the answer for part A, which is our general temperature distribution. Is it a function of R? Well, where is R? R is right there. But there's also R1, R2, T1, T2 in the equation. Okay. Then the next is, what is the rate of heat transfer through the layer? What law do I use right here? Fourier's law. And then we just cancel some terms. There it is. You could box it. Then part C says, can you identify a thermal resistance? You say, well, Q equal to delta T over R. Let's just do the name calling. And that R is 1 over R1 minus 1 over R2 divided by 4 pi K. Okay. If you use it a lot, you'll remember it. If not, there's an equation sheet. But this is how you derive it. So there's our, out of the table 3.3, you'll notice that for the slab or the cylindrical wall or the spherical shell, I would call it, not a wall, but a shell, you have the thermal resistance. There's a number of other things, starting equation, temperature distribution, heat flux, heat rate. But L over Ka, kind of a bottom line for the thermal resistance. The natural log of R2 or R1 divided by 2 pi KL, that's the natural, that's the thermal resistance for through insulation. And this one for the insulation, a spherical tank, 1 over R1 minus 1 over R2 over 4 pi K. So you can solve problems in radial systems as well. Let's take a look at this problem. Hot water flows through a 3 centimeter diameter thin-walled copper pipe that is wrapped with 2 centimeters of insulation with the thermal conductivity of the insulation given. Before I move on, that first sentence is a lot to digest. Can you make a sketch? And we have water flowing in a pipe, right? And there's some key words right here. What's thin-walled mean? Neglect the conduction through the high conductivity copper and neglect the thickness of the copper. So there's no resistance to heat transfer offered by the copper. And so if I was to say, here's the center line of the pipe, right, and it's running down that way. This goes out to an R1. So what is R1? It's the same as the inner radius or the outer radius of my copper thin-walled pipe or tube, okay? So what is R1? I know this is trivial, but I've graded a lot of exams. The information's here. I'm going to pause. I'm going to walk around and see. You write down what is R1 and then what is R2. R1 and R2. All right, so a lot of people were able to say the diameter inner is given to be 3 centimeters. I'll divide that in half and I'll get 1.5 centimeters, and then I'll put that over in meters. I'll put 0.015 meters. That's all very good for R1. Then you have to struggle with what's this information about 2 centimeters of insulation. It's the thickness of the insulation. So it's T, the thickness of the insulation, is 2 centimeters. So if I wanted R2, it would be R1 plus the thickness of the insulation, which means that it's 3.5 centimeters for R2, which is R2 is equal to 0.035 meters. I know that's error prone. Please don't make a mistake like that on the exam. All right. Well, did I make a mistake? Some people made some mistakes when I walked around. Please get it down. You're good. The water is at 80 degrees C and a convection coefficient of 35 watts per meter squared degree C on the inside of the pipe. So that's T infinity of the fluid in the inside, and then there's a convection coefficient to get it into the wall of the pipe, etc. The surrounding air, so we have air out here, it has a temperature T infinity on the outside of 25 degrees C and a convection coefficient of 20 watts per meter squared degree C. And so what was this one? This was T infinity on the inside of 80 degrees C and H on the inside of 35 watts per meter squared degree C. All right. Now, calculate the rate of heat transfer per unit length of the pipe. Okay, what symbol am I going to use for the answer that I'm trying to get? Q over L, but what's L? L is this length. True? And some people may say Q prime, which is good. Q over L or Q prime. So what I do is I say, how do I calculate Q? Wouldn't it be sub delta T divided by some overall resistance to the heat transfer going from the hot inside water to the cool outside air? That'll be a sum of resistors. True? Okay, the same thing you can do here. Do I work with L as a variable, or do I just pick L to be 1 meter, and then I know that everything I'm going to calculate, it'll be like on a 1 meter basis? Just like before, it works either way. You just have to be consistent with what route you start in your analysis. Okay, so I make a little network, and I have, what are at the nodes of the network? Temperatures, T infinity on the inside, T infinity on the outside. What is this one? This one is 25 degrees C. Got too much junk in the way. 25 degrees C, and this one is 80 degrees C. Do I really have two other nodes? What do they represent? Temperature 1 and temperature 2, which is the surface temperature of the inside of the insulation and the outside of the insulation, T1 and T2. So this is going to be 1 over H1A1, 1 over H, this is inside, outside, area outside, right? And what's this resistance to conduction through it? It had a natural log, R2 divided by R1 divided by, I know that you have the equation sheet available, but is that the right equation? You're helping me over here. Is that good? Very good. Now somebody says I'd like to replace that A1. So what is the area on the inside? 2 pi R inner L, and we just solved for R inner. How about the area on the outside? 2 pi R2 L, and we just solved for, did I call this, that's R1 and R2, R1 and R2, okay? Right? I think it may be easier just to pick L as one length, 1 meter, and then we know everything's now based on the flow per one length of 1 meter. Okay. So what I'm going to do is I'm going to calculate the resistances here. So we put a 1 over H. So we have 1 over 35. Then you have times 2 times pi times 0.015 times 1. Plus, we're going to have the natural log of, you don't have to put all the, you can put centimeter over centimeter at this point, 3.5 over 1.5, that'll work, right? Or you can put 0.035 divided by 0.015, that'll work. 2 pi, the K, the thermal conductivity of the insulation, 0.05, and the L of 1. And then we're going to have 1 on the convection on the outside. That's 20 times 2 times pi times 0.035 times 1. And we sum that up. But before I do that, I'd like to make the intermediate calculation. This is 0.30315. This is 2.69703. This is 0.22736. When you add them up, that's 3.2276. This would be degrees C per watt, and you go and make the calculation for comparison purposes. This represents 9.4% of the resistance. This, because they're all in series, 83.6%. Hey, that insulation's doing a pretty good job. It dominates the resistance. And this is 7%. Okay. So you could probably increase the thickness of that insulation some more and cut down even further on the rate of heat transfer. So we calculate that we get Q, which is delta T over R. It's 17.0 watts. And then we recall, oh, everything was per meter. So there's your final answer. Does that make sense? 17.0 watts per meter. So use the network to help get straight and do your bookkeeping. Let me take a look. Last slide. Just a reminder that we don't cover all of Chapter 3. We just 3.1 through 3.5. Any questions? Thank you very much for your attention. I'll take your question down here.